In this session, we will provide an overview of the fundamental concepts necessary to understand Ethernet and TCP IP networking. We will show how basic network elements operate in interconnecting, sending, receiving, and processing information. We will first define some basic terms dealing with networking fundamentals before turning to the OSI 7 networking layers reference model and describing the role of each layer. Following that, we will look in more detail at the Ethernet physical layer and the Ethernet data link layer, which are the first two layers of the OSI model, as well as the role of VLAN or virtual LAN tagging, which is also a layer 2 technology. In the second session of the networking fundamentals, we will cover the layer 3 IP and layer 4 TCP UDP of the OSI model. A bit, represented by a lowercase b, is a binary digit and the smallest unit of digital data. It can take on one of two values. For example, it can be either true or false, or it can be 0 or 1. A bit is said to be set if its value is true or 1, and it is reset or clear if its value is false or 0. A bit is a format in which data is processed by computers. A byte, represented by an uppercase B, is equal to 8 bits, which is also called an octet. Historically, a byte was the amount of bits needed to represent one character of text. It is the unit that describes the amount of data on a network or in a file. Kilobits per second, or thousands of bits per second, and kilobytes per second, or thousands of bytes per second, are ways to measure bandwidth on a data transmission medium. Bandwidth is the amount of data that can flow in a given time. Here is a summary of the previously mentioned measurement units and their relationships to each other. A higher bandwidth is more conveniently expressed in megabits per second, which are millions of bits per second, or in gigabits per second, which are billions of bits per second. The Open System Interconnection model, also known as the OSI model, was designed so that any two systems connected on a network can communicate, no matter where they are connected or what software they are using. The OSI model has 7 defined layers, each with well-defined headers, trailers, and interfaces. Layer 7 is the application layer, which is the location of the user applications, such as email, FTP, and HTTP. The presentation layer is Layer 6, which deals with differences in data representation. The session layer is Layer 5, where communications between applications across a network is controlled. Layer 4, which is the transport layer, adds reliability to the transport from end to end. The network layer is Layer 3, which makes certain that a packet sent from one device to another gets there in a reasonable period of time. Routing and flow control are also performed in Layer 3, which is the lowest layer of the OSI model that can remain ignorant of the physical network. The two layers that we will deal with in this presentation are the data link layer, which is the second layer, and the physical layer, which is the first layer. The data link layer gets data packets on and off the wire, and deals with error detection and correction, as well as retransmission. The physical layer is where the cable, connector, and signaling specifications are defined. The TCP/IP model, which is the most widely used communications protocol, is similar but not completely identical to the OSI model. Both models use a layered protocol stack, but the TCP/IP stack has less layers than the OSI stack. In the TCP/IP stack, the application layer combines the OSI application, presentation, and session layers. However, The transport and network layers in the OSI stack are similar to the corresponding layers in the TCP/IP stack. The data link and physical layers of the OSI stack map into the Ethernet physical and Ethernet data link layers. In this example, the application is to send an email. In the application layer, Simple Mail Transfer Protocol, or SMTP, collects the data and formats it for sending across the network by adding a SMTP header. SMTP then forwards the data to the transport layer. On the transport layer, the Transmission Control Protocol, or TCP, receives the data from the application layer and segments it so it can be handled by the recipient host and to ensure that the data is not lost. TCP adds a header to the segment and passes it to the IP layer. On the network layer, Network Protocol, or IP, receives the segment from the transport layer and adds destination and source host address information as the IP header. On the data link layer, Ethernet Media Access Control, or Ethernet MAC, adds a hardware address information and an error verification mechanism, which is the frame check sequence, or FCS. On the physical layer, Ethernet 802.3 formats the data bits so that they can be transmitted on the physical media, which is either wire or fiber. On the receiving side, the remote device performs the following operations. On the physical layer, Ethernet 802.3 receives the bits, which are zeros and ones, and passes the bits to the data link layer. The data link layer checks the FCS to make sure that the data is not corrupted. If the FCS is correct, the layer then checks the MAC information to make sure that the frame is addressed to the host. Then it strips the MAC header and the FCS and passes the data to the network layer, where IP verifies the source and destination IP addresses of the packet and reassembles the data in order. If the data arrived out of order, the IP layer strips the packet out of the IP header and passes the data to the transport layer. On the transport layer, TCP receives the data from the IP layer and checks that the data is destined to the SMTP application layer and that no data is missing. Then, it passes the data to the application layer where SMTP formats the data in a way that can be understood by the end user. Ethernet was invented by Robert Metcalfe at Xerox in 1973 and patented in 1976. IEEE standardized the 802.3 Ethernet in 1983, and the ISO standardized it in 1989. Ethernet in Layer 1 generates and detects voltage, or in the case of fiber optic transmission, pulses of light, so as to transmit on the physical medium and receive signals that are carrying data. The Ethernet standards have been defined for speeds varying from 10 megabits per second to 10 gigabits per second, and the newer versions even support speeds up to 100 gigabits per second. The full specifications can be found in the IEEE 802.3 standard documents. This table shows the two Ethernet standards 10 base T and 100 base TX. 10 base T has a transmission rate of 10 megabits per second and transmits media over 100 meter long Category 5 unshielded twisted pair cabling. 10 base T requires 2 cable pairs and uses RJ45 to connect the Category 5 cables. 100 base TX also transmits media over 2 pairs of 100 meter long Category 5 unshielded twisted pair cabling, but it has a transmission rate of 100 megabits per second. This table shows some gigabit Ethernet connection standards. 1000 base T transmits using 4 pairs of Category 5E unshielded twisted pair cabling. Like the previous Ethernet standards, 1000 base T uses RJ45 as a connector and its maximum segment length is 100 meters. 1000 base SX is a fiber optic standard that transmits using 850 nanometer laser on multi-mode fiber. Its segment length can reach up to 220 meters on 62.5 micron fiber, or 500 meters on 50 micron fiber. It uses SC or LC optical fiber connectors. 1000 base LX uses 1310 nanometer laser on single-mode fiber. Its segment length can reach up to 10 kilometers on 9 micron fiber. 1000 base LX also uses SC or LC optical fiber connectors, as does 1000 base ZX. 1000 base ZX uses 1550 nanometer laser on single-mode fiber and has a maximum segment length of 100 kilometers. This chart shows the 10 gigabit Ethernet standards that use optical fiber. These Ethernet standards transmit at a rate of 10 gigabits per second. Two main versions exist, the LAN and the WAN. The LAN physical layer is compatible with the other Ethernet LAN standards, whereas the WAN version was designed to be compatible with OSI 192 Sonnet. The next three 10 gigabit Ethernet standards have a LAN physical layer. 10G base SR, where SR stands for short range, uses 850 nanometer laser on multi-mode fiber, and it has a maximum segment length of 300 meters. 10G base LR, where LR stands for long reach, uses 1310 nanometer laser on single-mode fiber with a maximum segment length of 10 kilometers. Single-mode fiber is used for communication over longer distances. Like the previous Ethernet standard, 10G base LR has a LAN physical layer. 10G base ER, where ER stands for extended reach, uses 1550 nanometers laser on single-mode fiber and supports a maximum segment length of 30 kilometers. 10G base ER also has a LAN physical layer. The next three 10 gigabit Ethernet standards shown on this chart, however, have a WAN physical layer. The WAN PHY used in 10G base SW, LW, and EW is used to interoperate with OSI 192 Sonnet equipment, which is used to transport the 10 gigabit Ethernet traffic over existing Sonnet equipment without needing to remap the traffic into Sonnet frames. Other than the difference in the physical layer, 10G base SW corresponds with 10G base SR, 10G base LW with 10G base LR, and 10G base EW with 10G base ER. The RJ45 plug is used to connect unshielded twisted pairs to Ethernet devices. 10 base T, 100 base TX, and 1000 base T all use the RJ45 plug. Ethernet cables are normally straight through, which maintains the pin connection throughout the entire length of the cable. Straight cable should be used to connect different types of devices. For example, it can connect stations to hubs or stations to switches. Ethernet crossover cables should be used to connect devices of the same type, station to station, hub to hub, and switch to switch. With crossover cable, some pins on one side are connected to a different pin on the other side. Most modern equipment, however, automatically sense the connection and do not require crossover cables. The small form factor pluggable, or SFP, converts electrical signals into optical signals. It has the same properties as a GBIC, but with a smaller form factor. LC connectors are used to connect fiber optics to a SFP. The 10 gigabit small form factor pluggable, or XFP, operates at optical wavelengths of 850 nanometers, 1310 nanometers, or 1550 nanometers. Its applications include 10 gigabits Ethernet, 10 gigabits per second fiber channel, and SONET at OC 192 rates. XFP modules use LC connectors to achieve a high density. We will now look at the Ethernet data link layer, which is the second layer. This chart shows the Ethernet frame format, which represents how the bits sent on layer 1 are formatted. The preamble is a 7-byte sequence that tells the receiver to get ready for a frame. It is an alternating string of 1s and 0s ending in a 0 bit. The start of frame delimiter, abbreviated as SFD, is a byte that indicates the beginning of the frame. It continues the alternating bit pattern of the preamble and ends in consecutive 1 bits, so its pattern is 1 0 1 0 1 0 1 1. Then come two MAC layer address fields, the destination address and the source address. Each are 6 bytes or 48 bits long. This is the address of the network interface controller in the device, not the IP address, which is normally 4 bytes or 32 bits long. We will see the format of a MAC address later. Depending on the specification, the length type field can represent either the length of the Ethernet frame or the type of protocol being carried in the payload. If the value of this field is 1,500 or less, it will indicate the length of the data field in bytes. If the value is equal to or greater than 1,536, then the field is used to indicate the protocol carried in the payload, such as TCP, IP. The next part of the Ethernet frame is the data field, which can contain a minimum of 46 bytes and a maximum of 1,500 bytes. If this field contains less than 46 bytes of data, it is necessary to pad this field to reach the minimum number of bytes. Finally, the frame check sequence is a 4-byte cyclic redundancy check field that provides error detection for the frame. Because of the wide variation in the data field's possible size, the Ethernet frame data size encompasses between 64 and 1,518 bytes. The Interpacket Gap is a self-imposed quiet time appended to the end of every Ethernet frame, giving the network media a chance to stabilize and other network components time to process the frame. At a 10 megabits per second Ethernet rate, the minimum interpacket gap is 9.6 microseconds. At a 100 megabits per second Ethernet rate, the minimum interpacket gap is 0.96 microseconds. At a gigabit Ethernet rate, the minimum interpacket gap is 96 nanoseconds. At a 10 gigabit Ethernet rate, the minimum interpacket gap is 9.6 nanoseconds. To transmit traffic at the maximum rate, the frames must be transmitted with these minimum interpacket gaps. We will now learn how to calculate the maximum frame rate. We must first know the maximum data rate, which is indicated in the name of the standard. The second variable is the frame data size, which must be between 64 and 1,518 bytes. Finally, we must also know the overhead, which is equal to the preamble's 7 bytes, the starter frame delimiter's 1 byte, and the interpacket gap, which is 96 bits. The overhead is therefore 20 bytes or 160 bits. The maximum frame rate is equal to the maximum data rate divided by the sum of the data size and the overhead. Here are 3 examples of how to find the maximum frame rate. First, if 10 base T is being used, the maximum data rate will be 10 megabits per second or 10 million bits per second. Assume that the data size is 64 bytes or 512 bits. The overhead is 160 bits. 10 million bits per second divided by the sum of 512 bits and 160 bits equals 14,880 frames per second. This is the maximum frame rate. In 100 base T, if the data size is 64 bytes, the maximum frame rate is 148,809 frames per second. In 1000 base X, if the data size is 64 bytes, the maximum frame rate is 1,488,95 frames per second. If we take the example of gigabit Ethernet, we see that efficiency increases as the frame length increases. When the frame size is larger, more of the available bandwidth is used and the 96 bits of the interpacket gap become less significant. Looking at the chart, we see that when the data size is 64 bytes, 23% of the available bandwidth is lost. But when the data size is 1,518 bytes, only 1.3% of the bandwidth is lost. The actual frame lengths in a real network will constantly fluctuate, causing the bandwidth utilization to also constantly change. This principle also applies to 10 base T, 100 base TX, and 10 gigabit Ethernet. The MAC address is the unique hardware address associated with each device. It is 6 bytes long and represented in hexadecimal format. There are two MAC addresses on the Ethernet frame. The source MAC address identifies the sender and the destination MAC address identifies the receiving station. The first 3 bytes of the MAC address are vendor-specific and are assigned by the IEEE. The last 3 bytes are left to the manufacturer to assign. A MAC address is unique and burned in the hardware by the network interface card manufacturer. There are 3 types of destination MAC addresses: the unicast frame, the broadcast frame, and the multicast frame. A unicast frame is destined for a single station. A broadcast frame is destined for all the stations on the network. This is the format of a broadcast frame. Broadcast traffic can be very polluting because all the stations on the network receive and process it. A multicast frame is destined to a group of stations and is more efficient than broadcast traffic. This is the format of a multicast frame. A layer 2 switch is a device which maintains a two-way table that associates a physical port with the attached Ethernet MAC address. It reads packets, stores them in memory, and then forwards them out to the appropriate port based on the destination address. This happens simultaneously on multiple channels. The switch establishes a virtual connection to temporarily connect the source and the destination. Once the packets have been sent, the connection is terminated. The packets will only go to the port where the destination is located, with the exception of broadcast and multicast traffic. Broadcast traffic will travel to all of the stations on the network. Layer 2 switches do not look at the IP or Layer 3 addresses of the packets. They are only used in a LAN, where only local stations are sending and receiving frames. When connecting to the Internet or WAN, a Layer 3 networking device called a router will be used. This will be covered in the second Networking Fundamentals session. In order to avoid broadcast or multicast traffic, which pollutes all users and workgroups connected on a LAN, standard IEEE 802.3q defines the concept of a VLAN, or virtual LAN, where users can be grouped together by workgroup or department, instead of by location. A customer using a VLAN will seldom need to physically move equipment around or rewire the cabling scheme. When the network topology changes, the customer can simply use software to reassign the users or entire work groups to a different VLAN. The stations can all be in the same room, or they can be in different buildings. They can be connected to the same switches or to different ones. All the users that are connected to one VLAN will see each other's broadcast traffic, but none of that traffic can be seen by any members of another VLAN. In order to communicate to a station on another VLAN, a Layer 3 router is required. By restricting broadcast traffic to a particular group or area, a VLAN increases network performance. More importantly, a VLAN increases security because it requires a router before it can communicate with another VLAN. Membership in a VLAN is indicated by the VLAN tag added to the Ethernet traffic immediately following the address fields of the frame. The important fields in the VLAN tag are shown in this graphic. P, which has 3 bits, indicates the priority on a level of 0 to 7. The 12-bit vid field, which can take a value from 0 to 4095, identifies a VLAN to which the frame belongs. Standard IEEE 802.3 AD defines the concept of double VLAN tagging, also called Q-in-Q, which is used by service providers when interconnecting VLAN traffic from remote locations. VLAN tags are added when the Ethernet traffic enters the carrier's network, and they are removed when the traffic exits the network. The service provider can add a service VLAN or SVLAN tag to the traffic that already has a customer or CVLAN tag. The VLAN stacking process supports customer VLAN preservation over the service provider network and ensures a complete separation between traffic from different customers. In this first session on networking fundamentals, we defined some measurement terms and learned about the OSI model. We then looked at the Ethernet's physical layer's most common standards before turning to the Ethernet's data link layer, which is the second layer. We learned about the frame format, Interpacket Gap, the frame rate, and the MAC address format. Finally, we covered the concept of virtual LAN and its uses. In the next session, we will cover the higher layers of the OSI model. For more information, contact VX at 510-651-0500 or on our website at www.vxinc.com.